is Alessandro Marini, and thank you, Jay, for the nice introduction. As Jay said, I have something like 15 years experience using Ansys, and I'm here at Fluent KAUST taking care about the CFD business side. And today I'm here to introduce you to this application that is specifically for mesh generation, specifically for CFD, okay? And it goes under the name of Fluent Meshing. So this is one of the tools that is available in the Ansys suite, in the Ansys portfolio, to give you, let's say, the opportunity to generate the computational grid for this specific application within an environment you already are familiar with, most probably. So it's Ansys Fluent, basically. So there is a, let's say, a different mode of using Fluent that is for mesh generation. So I want to give you a brief introduction in that regards, but I want also to give you, let's say, an overview, because as through the introduction by Jay for this presentation, he was mentioning that actually there are many other tools. So I want to give you an overview, a full overview first, very quickly, what is available, what you probably went through in the past, and what you're maybe trying to exploring. And what I want to show you here is something specific into that. And I want to guide you through the usage of this new way to generate the mesh, basically, when we are approaching the CFD analysis using Ansys Fluent. So the new Fluent Experience, as it is called. And then I will give you a brief introduction about Fluent Meshing, how it works, how it looks like, and then we will go for a short, let's say, live demo, just to give you a flavor how it works, how it looks like for real. Okay, not just through the slide, but definitely through kind of hands-on session done by me, and so you can appreciate how easy it is to go through, how easy it is to generate the mesh, what kind of nice quality mesh we can generate, basically with no effort. So let's start to give you an overview of what is the solution by Ansys for the mesh generation applied to CFD. So let's focus mainly on CFD, but it's not just limited to that actually, because maybe you already know, maybe you already use this kind of tools. Some of them probably you heard about. So what is the Ansys solution for mesh generation? So this is the quick overview. Okay, we have tools. Let me just change the pointer here. Okay, so we have tools that are dedicated to fluid dynamics. Okay, Fluent Meshing, for example, is one of this. And this is what we are gonna, let's say, dig into in this presentation. But maybe you already use this Ansys meshing. So Jay mentioned that some time ago a training about this tool was given. So you're pretty much, let's say, this is a general purpose way to generate the mesh. And it can be this kind of unstructured mesh, but the main, let's say, strength of this Ansys meshing is the fact that it is multi-physics. So we can use the same tool for both CFD and mechanical applications. So maybe you're familiar with that because you're already doing something in this direction. So multi-physics approach, or let's say this is the standard, or let's say not the standard, the classical way used in the past to generate a mesh for CFD application, but it's not limited to that. This is what I mean here. So if we go more into the details of the CFD, then we have these other options available. One is Fluent Meshing, as I said, again, is an unstructured, fully unstructured way to generate the mesh. And there are two other tools available, main tools available, let's say. One is for turbo machinery application, and it's called TurboGrid. And then we have another couple of applications, actually. It's not just one. There are two different applications. One is Icmcd, and the other one is Spaceclaim meshing. So if you're familiar with Spaceclaim, you know Spaceclaim as a tool for geometry preparation to, do some kind of the featuring, or maybe if you're interested to generate a mesh, a geometry from scratch, you don't need to go for a CAD system, but eventually you can use some tools available in the Ansys portfolio to generate the mesh, and this is Spaceclaim. Probably you heard about that, or maybe you're already familiar with that. But not everybody knows that inside Spaceclaim there is a, let's say, a mode, an additional mode that is giving you the opportunity to generate structured mesh in a similar way that Icmcd, like these structure blocks and hexa elements like this. So this is to give you a full overview of all the tools available. So what are the advantages or disadvantages or the utilities that can we go through using this kind of tools? So Ansys meshing, there was kind of recent update, and let's say in 2019 or 2, the new ribbon interface is available, and this is something common through all the Ansys tools in the portfolio. And you will see also the same in Fluent, for example, and we will see later on also in Fluent Meshing. So this is something of common ground for all the Ansys tools with this ribbon. So also Ansys meshing recently has been, let's say, updated into this new kind of interface. One thing I want to highlight here is the way the developers are pushing into the direction of Ansys meshing. So basically the development is more oriented to the structural side. So this is the reason why the CFD community using Ansys is migrating into something different. And this something different is Fluent Meshing. So this is why we are giving this kind of focus to these tools, this tool today. And here you can see a brief introduction to what are the main features of this tool. So it can handle very large and complex geometry. Yes, this is true. I can tell you because I went through this already. So this technology is there for the last, let's say, 2-3 years in this form. And I tested many times, and I can confirm that a large geometry can be easily handled with very little effort, I would say here. And the mesh regeneration, the process of mesh generation is quite robust, and is highlighted here at the top right side. When we are talking about robust mesh generation, capability to handle large geometry, that means we can generate very large meshes efficiently. So we can exploit a lot what is the parallel meshing. So this is something that in the past was kind of bottleneck, if you think of it. If you're already familiar with the Ansys tools for mesh generation, there was kind of bottleneck into that. So basically when we are pushing on the performances to get bigger meshes, bigger models, high fidelity meshes and stuff like that. So we need to, speed up the process. And we want to speed up the process, as you are already familiar, using Shaheen. So we have all this kind of hardware available, but the software was not able to keep up basically with the hardware. So Fluent Meshing is going into that direction. So recently, the developers, let's say the last 2-3 years, the developers from Ansys, they started to develop this technology, taking an old existing technology and adapting to the new, let's say, requirements of the users, the new availability of the hardware resources. So still up to date, developers are pushing harder and harder to get more and more performances in the mesh generation. So now we are talking about 128 to 156 core with kind of linear scaling in the mesh generation. So this is unprecedented. This is something really, really good compared to what is available for the other tools and what was available up to a few years ago, looking at Ansys here. But it's not just limited to that. We are not just talking about performances here. We are talking about also technology, new techniques to generate the mesh. So Fluent Meshing is not limited to standard approaches for unstructured mesh. So we are not just talking about tetrahedral mesh, tetrahedral with prisms, tetra X core. So if you're familiar with Fluent, maybe in the past you were generating the mesh in a tetrahedral way, and then we were transforming the mesh. You were doing a transformation, so you were transforming the tetrahedral mesh to polyhedral mesh. So that was an additional feature you were using before performing the simulation. So that was done by Fluent before starting the simulation. So now what Fluent Meshing is giving you is the opportunity to generate native polyhedral mesh. Okay, so you generate directly the polyhedral starting from the geometry. So you fill up the volume using polyhedral cells from the beginning. So this is a big advantage. And it's not limited to that. So as you can see here, but I will explain a little bit more later, we have this kind of hybrid meshes where we have a combination of polyhedral and hexahedral elements. Always unstructured, there's nothing structured here, it's completely unstructured. But here, this kind of new methodology to generate the mesh that is called PolyX Core is giving you a lot of advantages. And we are going to explore that later on. So let's keep it pending for a moment, but this is just to give you a little bit of that flavor. So as we already mentioned earlier, so we have a full, in this way, using this Fluent Meshing, we have a solution, a complete solution from CAD import to mesh generation, to the setup of the simulation, to the run of the simulation itself, to the post-processing at the end, in the same environment. So we have a new experience. This is called the new Fluent Experience. And again, I will give you a little bit of details later on, but this is a unique solution now for Fluent, for Ansys. And this is going to, close some gap if you're looking around with respect with the competition. So there was something in the market, and now Ansys kind of closed that gap. So it's giving a solution in the same way that other competitors are given, like everything is done in a single interface, basically. But the way we are doing it in Ansys is kind of more efficient. Okay, and we will see, and you will be able to see that in action very soon. So we have a full support on Linux and Windows platforms. So this is okay, and everything it can be completely automated. So if you think about using Ansys tools in Workbench, so we already have an idea about automation there. So we have systems, they are connected, so we can create a workflow from A to Z, and we can run automatically through Workbench. But Fluent Meshing can go beyond that. So basically, we can use some scripting or journaling in order to customize the Fluent Meshing process. So we can create customization of the process, how to generate the mesh, and so we can have full control on that, and eventually we can run through the batch line, to the command line in batch. So this is something that you would like, because as I can imagine, you're running on Shaheen, everything will be handled remotely, so you can submit your scripts to run the Fluent Meshing very easily. Okay, and everything can be customized, so it's very flexible as well. Another good thing that I want to highlight here for the first time is the fact that Fluent Meshing is based on workflows. So maybe you captured when I was talking a little bit earlier that this is not a really brand new technology. This is something that is existing for many years, but in the last 2-3 years, very recently, I would say, the developers started to, let's say, redevelop again. So basically, there was this technology that was called T-Grid, okay? And this T-Grid was not really, user-friendly or very straightforward to use. So the developers, they moved into the new direction of generating kind of streamlined, easy to use, very user-friendly workflow. So the idea of workflow is to give a new perception to the users whenever he's trying to generate a mesh using this tool. So basically through these workflows, and we will go into see in action one of them, you will appreciate that it's very easy. It's completely guided, very easy, just a few inputs, and then you get a nice mesh, very high quality mesh, basically with no effort. So this is one of the big advantages of using this kind of technology. So we have workflows already there. So as you can see here, there's a small example. Everything is already set. We just need to give a few inputs and everything will be taken care of automatically, basically. So as you can imagine, everything is pretty much already there. We just need to provide a few inputs. So it's very fast to learn how to use it. We can automate everything and it is persistent. So at the moment I want to, oh, I forgot, I need to include some more detail in the mesh. So I want to change the local sizing, for example, or I want to change one feature of the mesh. So I can go back, make a modification and rerun the workflow entirely with a single click, basically. I don't need to do everything over and over again. So the persistence is there, automation is there, it's very easy to learn. So you start to appreciate that. And if you want, I can give you my direct experience. So basically, this is the only tool I'm using as of now when I'm generating the mesh for CFD application, and this is what I'm doing on a daily basis. I'm just using Fluent Meshing. I forgot basically about all the other tools available because of these many advantages that is bringing me. And I hope this will be helpful also for you guys to improve your experience, to improve your productivity, basically, when you're performing CFD simulations. So just to complete the overview, this is another tool that is called TurboGrid. This is specific for turbo machinery applications. So in case you're dealing with turbo machinery, pumps, turbines, compressors, stuff like that. So basically, you might already know that the mesh is very important, even more important than usual, I would say. It's always important, yes, but for, let's say, turbo machinery application, we might need to have some regular pattern. And this regular pattern of the mesh is given by structured hexa elements, structured grid with hexa elements. So TurboGrid is giving you very, let's say, straightforward way to generate a mesh for turbo machinery application. So basically, there are already templates in the core of the software that will recognize the structure of the, let's say, the layout or the topology, let's say, of the turbo machinery, and then automatically will be able to generate the mesh with very high quality, and it can be completely scalable. So we can, let's say, change the parameters of the mesh, but keeping, let's say, the quality. When you're pushing, let's say, on the size of the mesh to get more and more refinement, but let's say the quality itself is quite persistent and scalable. And this is another big advantage when you're dealing with this kind of problems. And recently, as you can see here in these pictures, I just mentioned this is a full hexa tool, but actually in the last few releases, this technology has been, let's say, developed even more in order to be able to capture, let's say, non-conventional topology. So if you think about a turbo machinery, for example, this is the tip of a turbine blade. So you want to see the cooling. And then we have this kind of topology here. And in this case of generating automatically a full hexa mesh, that was not really possible to do that. So we need to do manually some some decomposition here and there to put together pieces of several components of different parts of meshes, if you want to, in order to replicate this kind of object. But now it's not necessary anymore. So TurboGrid has been developed in order to capture also these things with a hybrid approach. So let's say in the main path line, in the main passage, then you have a full hexa mesh, very nice, very accurate, super refined, as you like. But here, when the topology, let's say, is more complex than a single, simple blade passage, then you have this hybrid approach that is going, the tool is able to capture these details with a non-structured mesh, and the mesh will be conformal at this stage. So this is another tool available. Another tool available, is, let's say, is one of the oldest available in the Ansys portfolio. It's Icmcd. It's well known in the scientific community for many, many years. And it can be used to both, let's say, unstructured meshes, but the main strength of Ansys CFD is the block structured hexahedral mesh. So basically, you can generate this kind of meshes using a different strategy. So it's a blocking strategy. So you need to give the tool an idea how the topology it is. So you need to work a lot on this. So this is the reason why, let's say, it's very powerful. This tool is very powerful, but it's not really user friendly. So we are moving to the direction that we want to spend less time and we want to have very high accurate mesh. So we need to find different ways. So Icmcd is there, but let's say, unfortunately, is not used that much anymore because of, let's say, modern times, okay, modern times requirement. Fast generation and high quality. So we can work a lot on this, working a lot using this Icmcd tool to get a very high quality mesh, but maybe we take 1 week, 1 month to develop such kind of mesh. Nowadays, for example, with Fluent Meshing, we can generate super accurate meshes with a few clicks, and that will take maybe half an hour. So you need to start to think, where should I put my efforts here? So maybe it's better to, generate an unstructured mesh and spend more time to check what is the result, actually. So let's say we have other ways, but still, this is part of the portfolio, so I want to mention that. So this is Spaceclaim meshing. This is the last one available, the last tool available in the portfolio. This is very recent. As you can see, the first release for fluid dynamics application is 2020 R1, so we are talking about 1 year ago. So we have capabilities. Basically, a lot of features from Icmcd has been migrated into Spaceclaim. So you can generate them into geometry in Spaceclaim, and at the same time, you can create hexa mesh, for example, in the same way you would do using Icmcd. So very high quality hexa mesh, but again, the efforts required to the user are quite high. So this is, let's say, can be a problem, okay? And it's limited to Windows only. So this is another thing that we need to take into account. And if you want to script, we can script. But again, the efforts required to the customer, to the user, sorry, is very high. So again, it's not completed, it's still in progress. So this is a very new technology, as you can see, and it's still under development. So maybe in the future will be mature enough to give us an extra opportunity. But I just want to, give you the full picture here. So now you have the full picture, and in the way I was exposing this thing, you can already understand that this is what is my preference basically here. So this is the reason why now I want to give you an overview of the Fluent user experience. So what is the Fluent user experience? So a new modern look to Fluent to do CFD more efficiently. Okay, so a new interface when I have less click to do, basically. So I can speed up my process in meshing and setting up the simulation and experience my simulation time and the post-processing. So this is a development that is not just related to the Fluent experience, the solution part itself or alone, but also for the rest of the pre-processing and post-processing. So if we are going to focus on this, I want to show you something. So new look, when we are talking about new look, is the new interface, basically. So we have a new interface when you have this tab at the top. So again, this is something common now in all the Ansys tools available in the portfolio. So we have a set of tabs and sub-tabs here that we can navigate and we can see all the commands available. But this is just one thing. Another thing is themes. So we can change the theme. So we have the new, this is the, let's say, the standard, new standard for Fluent. And this is one of the most recent updates. So we have also a dark theme. It was, let's say, a request, a lot of requests from the customers to have a dark theme. So here it is, finally. And then we can customize everything. Everything is customized. So we have, let's say, a preset of layouts, okay, and we can pick up one of those. And then we can change everything, basically, the location of the windows, the panels, the colors, the background, everything. So it's completely customizable. And another important thing is the quick help and search. So here, as you can see, there is a section on the top of the toolbar. Then we have a quick selection or a quick search, so we can go directly to the documentation. But at the same time, we have a kind of shortcut to the main commands. So it's like, I forgot, where is this command? How can I call this command again? So here in the quick search, I can find the location in the interface or through the command line here in the text user interface, how to reproduce something, okay? So this is just to give you a flavor of the new look. But what about the integration? What about this seamless experience from CAD import to the solution? So this is something I want to show you here. So just to give a focus on the pre-processing side. So we need to think that now we have something available in Fluent that is giving us the opportunity to generate the mesh. Okay, and this is the main target. We want more accurate results in less time. So how we can achieve this? So you should imagine that basically everything now is like well organized. So we are going to swim and we have the swim lanes. Everybody is in the swim lane. Nobody is disturbing each other. So everything is nice and coordinated. So we need to think about pushing forward into that direction in the same way. So basically we have workflows, and in the workflows we have tasks, and the task, each and every task is like the swimming lane. Okay, so everything is guided, so we need to go straight forward, straight back and forth into the swimming lane, for example. So everything is already there. Minimum input, we have status that are telling us everything is fine, a green tick, there is a warning with an asterisk. I need an input, this yellow light bulbs, or there is an error, there is a warning. So it's a red exclamation mark, for example. So through this simple coding, color coding, we can understand what's wrong or if everything is going all right. And all these tasks are guiding us. So these are tasks in sequence. We need to go from A to Z, from the top to the bottom, to reproduce, to create the mesh. So everything is there. So we just need to give a very few input, basically. And we can customize everything here. So if you are not happy about this workflow, eventually we can create our own workflow. So we have flexibility to change it. And when we need to change something, it's robust. So the moment I say, okay, I got the mesh, but I'm not happy because I need to change something. I'm not happy about the sizing. I want to change it. So let me go back, change this setting, and then update the mesh once again in one single shot. And as I mentioned, it's like we have a minimum set of input to give. And there are like questions like this, what you want to do with very few selections available. So it's very easy to pick up with this tool. So you will see. And yeah, another thing is like we can customize, yes, but we can also record. So basically we can create journaling, and then we can reproduce the whole process in batch eventually. So this is another important thing to remember here. So here, just to give you a flavor, what is the new Fluent experience? Here you see the comparison of generating a mesh in the old way and generating a mesh in the new way using Ansys, Fluent Meshing. So basically in the past, as I mentioned, this is an old technology, and this old technology was already there somehow. So we can use that, we could use that. And as you can see here, there is a lot of interactions, panels. So I didn't even finish to describe this. And as you can see here, the process is already done. With a new Fluent experience, there's no dialog boxes popping up, just a few clicks and you get your mesh done. Here, a lot more of clicks, many dialog boxes. So it's not really user-friendly, not straightforward. Users were getting lost using this technology. So this is the idea behind these workflows. So we have a tool that is there in Fluent and is giving us this kind of solution. Compared to the past, we have 70% faster and 50% less hands-on time. So you can see we are gaining a lot just on the meshing part, just on the meshing task. So this is one of the biggest advantages. Very user-friendly, straightforward, and fast. And this is the final stage. Okay, so we start from the geometry. We, for example, generate the geometry using Spaceclaim, or we imported the geometry from a native CAD format into Spaceclaim. We did some defeaturing, we prepared the geometry, and then we are ready to go for the simulation. So what we need to do is to import the geometry from Spaceclaim into Fluent. And this is Fluent in meshing mode in this case. So we import the geometry, and then we generate the surface mesh. So we need to create a nice representation of the boundary of this geometry. And then we need to input what we want to do with this. So we want to extract, for example, the fluid domain. So this is something we can do in Fluent Meshing. So as you can see here is that this is a geometry that represents a solid object, but we want to perform some CFD. So where is the fluid domain? So in a classical approach, if you remember, for example, you were using Spaceclaim or Design Modeler, extracting the fluid domain and meshing that fluid domain in Ansys Workbench meshing. Okay, now we don't need to do that. Okay, we can do that still, but we can do something else. So we have more flexibility in that. It's not necessary to import into Fluent the fluid domain. We can extract the fluid domain right there. So this is one of the many advantages of using this kind of tool. So we generate the surface mesh, and then we say, okay, we are just limited. We're just focusing on the CFD side. So we extract the fluid region. As you can see here, now we can see only the fluid region, and then we can mesh it. And here is one of the, let's say, options available. So it's a polyhex core mesh, and I will show you later on a similar example. But here we are still in Fluent, and then we can set up the model, giving the boundary condition, giving the numerical setting, run the simulation, and finally we can extract the result. So everything in the same environment. Okay, this is Fluent, only Fluent. We start from the geometry, we import the geometry, and then until the result and the post-processing, we just stay there in Fluent. And this is again, the new Fluent experience. What is Fluent Meshing? Just to give you a few more details, okay? This has already been covered many times. I explained this or I mentioned this. So Fluent Meshing is Fluent, is nothing different. It's Fluent in a different mode, okay? It's a meshing mode and there is solution mode. So same environment, same window, same interface. So we get, more comfortable working in this way. It's not like I have a bunch of tools and I have to open many interfaces. I have to transfer the information from one tool to another. No, everything is there in the same single interface. So this is one of the biggest, let's say, advantages from the user experience point of view. I already mentioned we can mesh, we can handle basically large complex geometries. And the big advantage in doing so is due to the, let's say, parallel opportunity, the parallel capabilities here, sorry. So we can mesh very complex geometry, very large model like aerospace and defense, or complex geometries like this. So we want to resolve the small details around this rider, and then we want to see the external aerodynamic or in oil and gas application. So any kind of industry, any kind of problem, any kind of complexity, we have power to do that. And so it's not just hardware power, let's say, but also the capabilities from the software. As I mentioned, Fluent Meshing is strong from that point of view. Another important thing to highlight is this poly-X core technology or mosaic meshing technology. And I will show you in the next slide what does that mean precisely. One of the limitations is Fluent Meshing is available only for pure 3D geometry. There's not a 2D version. If you're familiar with Fluent, you can run nice 2D application, for example, airfoils or 2D axis symmetric geometries like flat models. So flat model is not available in Fluent Meshing. So this is the one of the main limitations. But let me talk a little bit about this mosaic technology. Okay, so what is mosaic technology? So let's assume we have this combustor. Okay, this is an aerospace application, but how it works? What is the mosaic technology? What is the big advantage given by Fluent Meshing? So basically, we have this thing. Okay, first we need to think about polyhedral cells used to inflate the boundary layer. Why polyhedral? Because they are giving us very high quality mesh. And compared to standard prism with triangular base, they're giving us a lot of savings. Okay, less cell count here. In the bulk, in the core, as we say, hexahedral elements. So Cartesian hexahedral elements, very fast to generate, very accurate. So you will see this kind of approach will be extremely fast. Compared to other technology, this is a big advantage if you think of it. And then the mosaic will kick in. So basically, mosaic is the way these different layers of cells, the prismatic layers, inflation, polyhedral prismatic inflation at the boundary, on the walls actually, sorry, and the hexa elements in the core, they are linked through this mosaic technology that is nothing less and nothing more than connecting these elements in a conformal way with prisms. Sorry, with polyhedral, sorry. So we are connecting these different type of elements or any kind of elements in general using conformal meshes. So this is the mosaic technology, and it recalls this kind of artistic piece of art. So this is the main strength. So it's efficient to make it parallel. So if you think about the X-core meshing here, it will be in a blink of an eye, basically. And then the connection, that will require a little bit of time. Yes, I need to be honest here, but still, this kind of meshes are generated in a very, very short time, and the quality you can get out of it is extremely high. As you can see here, the detail of this geometry, the complexity, the transition. So we can also play a little bit with the transition. As you can see here, it's a octree Cartesian approach. But here you can see there's not this kind of transition, so we can also regulate the transition, conformal or non-conformal. So these meshes are both good for, let's say, Fluent, but in this case, eventually we can get a little bit more of accuracy. So it depends on the application, but we have, let's say, all the options available, so we can play a little bit with that. As I mentioned, we have good scalability, and this is the current range, okay, up to 256 cores of almost linear scalability, but developers are pushing harder and harder on this, of course. And because of this small amount of cell or reduced amount of cell count, then we have advantages also in memory and disk space when we are writing the results or when we are performing and executing the simulation. And then finally, to speed up the process. So we have a meshing speed ups compared to standard approach that is something in between 10 to 20 times faster. And the solve time reduction is somewhere around 30 to 50%. So there is a lot of advantages here. In terms of workflows, there are two different workflows available. As I said, there are ways to speed up the process to improve the user experience. And this is given by the workflow. So we have two different workflows, one for nice, clean geometries and one for dirty geometries. So when we have to deal with dirty geometries, for example, with gaps, leakages, sliver surfaces, so sometimes we need to go back to the CAD system and then we need to clean up the geometry. So that would take time. Okay, and sometimes we cannot solve 100% of the problems. So we need to find a way to, pass over this defect in the geometry. So the fault-tolerant meshing workflow is giving you this opportunity. So Fluent Meshing is able to use some wrapping technology to pass over these defects. So this is one of the approaches available. In case the geometry is perfect, all the connections are fine, everything is clean, there's no holes, there's no leakages, nothing, everything is perfect. So this is, just to give you an idea, is that exactly the same way you're preparing the geometry when you're generating the mesh using Ansys Workbench meshing. So the geometry has to be perfect. So we have the same approach here, but we can relax a little bit the conditions and take care about dirty geometries with a different workflow. Basically, we are wrapping the geometry with a surface mesh, and then we fill up the volume using this wrapping. So what I want to do now is just to switch for the rest of the time available to a quick demo on this application, the Watertight geometry workflow. Okay, so let me go here. Let me open Fluent. So this is the launcher, Fluent. We are in meshing mode. As you can see, there is only one single launcher. That again, there is only one.
Alessandro,
yes.
Hi, Zaidi. Will you be answering the questions now or after the demo? There are questions.
I think it's better to answer
after the demo.
Yeah, exactly, after the demo. Yes.
Okay, carry on.
Thank you, Mom. So as you can see here, we have a common interface for the launcher, so we can run Fluent in solution mode, but we can also launch Fluent in meshing mode. So we start from here because we want to generate a mesh. And here we set the number of processes we want to use for the meshing process or for the solver process. So in this case, I will use 4 cores on my machine, but you can use as many as you like for the meshing process, because the meshing process is not limited to the HPC licenses. Okay, so you can run as many cores as you like, keeping in mind that we are some, let's say, kind of limitation on the scalability. So it's up to 256 cores, it's fine. Going beyond that can be a little bit problematic in terms of scalability, but it's not limited to the amount of licenses you have in your pool. Okay, the solver, this is another topic, but for the meshing, there's no such limitation. Okay, this is something important I want to highlight here. So I set the working directory when I have my files. So now I'm ready to start Fluent Meshing. So as you can see, it's Fluent, okay? So the same interface, the same structure, just a little bit different layout, but still the same. So we have the ribbon on top. We have this panel here with the workflows. So here is the place when I set the workflows. Then we have the graphical user interface here. Nothing is there because I just opened interface from scratch. There's nothing there yet. And we have toolbars. So we can control the view here. We can control some fancy features here, and we have selections here available. And then we have the text user interface as we have in Fluent. So all the commands are available if we are, let's say, hardcore users. Otherwise, we go ahead with the interface. So first thing is like, okay, there are different workflows. Where are they? You can find here, workflow, this submenu, and we have several options. So in this demo, I want to go for the watertight geometry. So I'm assuming I have a nice and clean geometry. I click here and automatically you see there is a pre-populated workflow with many tasks, and I have to go to set these tasks to generate the mesh. I just want to give you an idea about the geometry. Okay, this is the geometry I want to take care of for this demo. It's a valve. We have 2 inlets and 2 outlets, and there is a body in the middle to regulate the flow. So I want to show you this in transparent, so you can see inside. Okay, as you can see, it's a solid body. There are several bodies actually, but all solids. I didn't extract the fluid domain because this is something I can do using Fluent Meshing. So I want to show you that. One thing I want to show you here is like the geometry is connected. So I already applied the shared topology here. So as you can see, the coloring here is telling me the geometry is good to go because all the components are connected. So there will be conformal meshes across the different bodies. So what I want to do here, going back to Fluent Meshing, is importing the geometry. So first task, minimum amount of input. As you can see, import geometry is just asking me, what is the format? It's a CAD. What are the units, millimeters? What is the file name? Okay, my working directory is geometry coming from Spaceclaim in this case. And as you can see here, we are importing geometry. So there is kind of triangulation happening in the background. So this is the representation of that geometry in Fluent. So as you can see, there is shadows and stuff. So for example, let's say I want to remove this fancy stuff. Okay, I can do this through the commands here in the toolbar. So in this case, in case the geometry is very complex, you will experience an improvement in the handling of the geometry. So I want to make it clear here, so it will be easy to understand what is what. Okay, so we have the 2 inlets, the 2 outlets, and the solid body. Okay, so let's start following the workflows. So next instruction to give is, would you like to add local size? So in this case, we can set local face sizing, proximity sizing, refinement, sorry, curvature refinement, bodies of influence and such. In this case, we have nothing as such, so we can skip this, but eventually, if you see here, if I switch to, would you like to add local sizing to yes, here is the panel. I have to input this information. So I want to change something in terms of what? Face size, body size. So these are the options available as I just mentioned, okay? So for the sake of time, just skip this, okay? Let's reply no to this question. Let's move to the next task. So we need to generate the surface mesh. So as you can see here, there are a bunch of cubes, big cubes, and if I zoom in, small cubes. So this is a representation of global sizing. Red boxes means global sizing, minimum size and maximum size. So as a rule of thumb, we may say, okay, this is okay, pretty much okay. But for example, I want to be more precise. So I want to follow another rule of thumb, like 10 elements in this diameter. If you're looking into a flowing through a pipe, then we go for something like that. So what I want to do is just to measure the distance on this diameter. So I can go back to the geometry, or I can extract this information here. So I select the filter on the nodes, and I will select 2 nodes on this diameter. Okay. Let me see if I pick up the right ones. This node and this node. And I want to measure this distance, so it's about 14 millimeters in this case. So it's very small. So this is my rule of thumb to follow. So my maximum size is 1.4. So I need to go back here and change this value. 1.4. And as you can see, the moment I press enter, I have an update of the CD. So now I have an idea about the maximum size. And if I zoom, I should see somewhere the minimum size as well. Here it is. So this is helping me to understand what I'm doing before generating the mesh. So let's assume everything is fine now. So let me click here, generate the surface mesh. And as you can see here, I have a full description of what Fluent Meshing is doing. And I have statistics of this surface mesh with all the statistics from each and everybody, the whole geometry, the count of the cells, the skewness. So in this case, it took something like 0.50 minutes with a maximum skewness of this value for the surface. So in this case, we are good to go. And one thing I want to do here is like, okay, and this is the representation of the solid part, but I need to extract the fluid part. So I need to tell Fluent Meshing this geometry consists of only solid regions. And this is the option here. This is the right option here. Do we want to extract the fluid regions? Yes. So we need to create cappings. So let me do that. As you can see here, I'm moving from the top to the bottom through each and every of these tasks. So I want to set, let's say through these regions, I'm using these regions for capping. As you can see, if I pass with the mouse, they will be highlighted in yellow in the graphical user interface, okay? I have this region, this region, this region, and this region here. So in Spaceclaim, somebody gave already the name selections. So I have already a smart naming to understand what is the inlet and what is the outlet. So I can proceed to specify the capping. So I have an inlet 1. This is the name I'm giving to this region. Select and I create the cap. As you can see here, there is a new branch coming up. And this is the capping that I just generated. And then I proceed with the inlet number 2, velocity inlet, group inlet 2, create a cap. Done. Here it is, second one. And then we have outlet 1 on this region. And this is a pressure outlet, for example, in my case. So I can select that zone type here. So I will find that later on already preset in Fluent. So this is helping me to set up the problem later on. So this is another advantage that Fluent Meshing is giving. And then the last, we have an outlet number 2, pressure outlet for this last one. Okay. So now I created all the cappings, as you can see here. So now, next task is create the regions. So here is the information about how many fluid regions you are expecting to find. So we know this is just a valve with 2 inlets and 2 outlets, but still one single fluid region. So this is the number I should put here. And I will create the regions and that will be extracted. As you can see here, this is the representation of the wet surfaces of the fluid region. This is what is inside that solid. And this is what I want to mesh, basically. Starting here, and now I can identify fluid region and many solid regions. So if I'm not happy with the names that Fluent Meshing is giving by default, I can double click and change. So everything customizable. It's not fluid, it's solid region. You can eventually change the things here. So now I'm happy with this. The fluid region will be called fluid and not fluid, 0 or some weird name. So I would like to make it like this. Next step, setting up the volume mesh. So first thing is how I want to generate the inflation. So here I can say yes or no. So no inflation, but it's not absolutely recommended for CFD application. Should be always yes. And we have many options available. Let's keep the standard definition of smooth transition in the same way. Let's say we can define the inflation in a Workbench meshing, so the same approach. Number of layers, the characteristic of the extrusion or the inflation, sorry. So we set this process and then we go to generate the volume mesh. And we have different ways to fill up the volume. So let's go, for example, for native polyhedral elements with 1.4 maximum size. And in this case, I can mesh solid regions or deactivate to mesh only the fluid region. In this case, let's go, for example, we are interested in some conjugated heat transfer simulation. So we can mesh in one shot both the fluid and the solid. Parallel meshing is activated by default. So all the methodologies here available are completely parallelizable. So we can just click here, generate volume mesh, and you will see in a few seconds, okay, this model is kind of small. Let me just show how to handle the mesh at the end here. Okay, here. Okay, so we have the mesh, and here again the statistics: 3.25K elements, 325K elements in less than 1 minute with a certain quality. So now everything is fine. So this is, let's say, a quantitative result. But in terms of qualitative results, of course, I can have a look into the mesh. So I can see the fluid region, the solid regions, the polyhedral elements in this section. Eventually, I can turn off and on the section generation. And I have this triad here, so I can move the triad to change the location of the section. So I want to explore how the mesh looks like here. Okay. So as you can see, it's very easy, very few clicks. But what if I want to change something? I want to show you very quickly the last thing I promised. Let me go here and say I want to coarsen the mesh. Wait, so I can speed up this thing. So for example, I want to edit this. Instead of using 1.4, I will go for 2.5 to make it very coarse, just to give you an idea. So now what I should do, I should go again one by one through the task and do everything again. No, I don't need to do that. What I need to do once the surface mesh is done, I just need to go till at the bottom and update the last. He's asking me, do you want to go through all this in one shot? Yes. So now you see mesh will be updated all along the task, the workflow automatically. And with this, I will be ending my demo. So
maybe can you show just a hex core one?
Yes. Hex
core, because that's important for everyone.
Yes, sure.
In meantime, there are some questions. Maybe you can just show and then we can take question and we can break. We are already 10 minutes over.
Mm-hmm. It's coming. Okay, now you see it's much coarser, but has been generated automatically. So now let me just change this polyx core and I will switch to the questions in the meantime. Polyx core update. I can ask this.
Yeah, questions.
Okay.
So the first question is that, are there any tutorials to help learning on Spaceclaim meshing?
There should be something. Yes, we can share that.
Right. Second question is, depending upon the problem, does Ansys automatically select the meshing options like Fluent or Spaceclaim or TurboGrid?
Not really. This is an input that has to come from the user because they are completely different tools. So we need to specify what tools we want to use. Yeah. So it's a selection by the user, basically.
Okay.
Based on the application, we pick up what is the best one.
Can I use the Ansys Workbench to generate geometry and then watertight meshing? Yes, I can answer. Yes, that's possible. Can I use the SolidWorks for draw the geometry? Yes, you can do that.
Yes.
Can you explain the growth rate option? Because by looking at the geometry, I can't see the growth rate effect. So I think it's visible here, growth rate.
The growth rate for the volume or for the boundary layer?
I think in general he's
Anyways, in
growth rate.
general,
Yeah, you can see.
basically, yeah, we can see here. So the growth rate defines the expansion between one element and the adjacent one. So basically, usually we need to think about going from the smaller size to the bigger size. So we have a local refinement, we have a boundary layer, something small, okay, a small element somewhere, and then we define a growth rate. So this is the speed, basically, of the increase of the sizing of the mesh. So we go from one small element to an adjacent bigger element to an adjacent bigger element with a certain growth rate. So for example, by default should be 1.2. So we are saying the height of this prism is, sorry, the height of this prism is 1.2 times bigger than the previous one.
Yeah,
And
I
so
think
on,
Alessandro,
and
he's
so on,
asking
so on.
where is the option, not the definition. So I think
Yes.
you can just show here. Yeah,
Yes, yes.
1.2.
Okay, so for the boundary layer is here, growth
Yeah.
rate 1.2 by default, or for the let's say the general settings, generate the surface mesh, growth rate 1.2. So 1.2 is the default. Okay.
All right.
A quick question. Asad Ali says, can we use Fluent Meshing and export the same mesh in mechanical or structure?
No, that's not possible.
No, it's not compatible. Polyhedral is just specific for fluid dynamics. For Fluent, just to be precise. It's not compatible with CFX, actually. Just Fluent.